Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm your host, Yogashri Pradhan. And with me here today, I have Erica Coenen from Reveal Energy Services. Today, we are going to talk about paper number 204179, and the paper description and the title is written in the description box below in the podcast and on the YouTube channel. I'm going to talk about Erica a little bit before we pepper her with technical questions. She's the VP of Operations for Reveal Energy Services. She started Reveal Energy Services a few years ago. She has a background in computational mechanics, and she has a PhD in fracture mechanics from Eindhoven University of Technology, where she's worked in applied research and manufacturing technologies. It is when she immigrated to the United States is when she made a switch to oil and gas, and the industry is extremely thankful for her that she has done that. So welcome to the podcast, Erica.
Thank you, Yoshi, for having me.
Well, I think usually the first question I ask is what companies do. But since I believe a lot of people know what Reveal Energy Services does, because you have over 100 clients when I last spoke with Cash, I thought that it would be right to just talk about what the paper is about for 204179. So could you walk us through the paper to understand the inter or interzone communication this is a Midland Basin case?
Sure. Let me first straighten history. I did not start Reveal Energy Services. I joined really from the beginning, and John Spicer was there just a little ahead of me. And what we did, we took the technology that Statoil had developed and spun that out and really commercialized that. And we have been working on offset pressure measurements ever since. And after about 2-3 years, we started integrating all kind of other diagnostics, and that's really where we're focusing on right now, and also launching a new product called Orchid, which is really geared toward integrated diagnostics. But this specific paper is indeed fully on offset pressure monitoring. And the unique thing about this paper, it was written together with Earthstone Energy on one of their wonderful paths. And when we write a paper together with an operator, we get a little bit more insight on that path than we would typically get if we only get the treatment data and only get the offset pressure data. And one of the very valuable pieces of information that was studied in this project was obviously the production data, because I think in a lot of papers that we see, we've either focused on analyzing the completion or we focus on analyzing the production, but we have to study those things jointly in order to find the link and really, start improving what we're doing. And I'm not saying that this paper is going to be the end-all paper. Actually, I think it's just a starting point of integrating, this completion diagnostics with actual production data. I would say this is really like the first step. The other thing that was really nice in this data set is that they did pressure interference tests. So once they brought the wells online, they had a quiet period of 30 days, just to have a little bit equilibration of all the pressures in the subsurface. And then they had one monitoring well located centrally on the pad, and they switched on. They start flowing from the wells around it in order to measure this inter-well communications in a systematic way. Very basic, but it was really that bridge from completion through early stage well interference towards long-term production. And long-term production, the longest production studied in this pad was 120 days. But that is really giving you a good understanding of how these wells will perform, long-term.
Awesome. I was excited to see production results when I read the paper, because I've read a lot of work on offset pressure analysis, and the question that always comes up is, well, what exactly are the results? Does production correlate with the offset pressure analysis? So it's really exciting to hear that you were able to integrate those production results and show that in the paper. I was happy about that. You mentioned about the offset pressure analysis, and the paper discusses certain signals. And I wanted to know, and I've seen in previous presentations they've talked about 4 different types of signals, such as the fluid migration, your poroelastic stress response, and in your compressive stresses. I was curious to know, how do you define a weak or a strong signal? Is it a total pressure increase, or is it a pressure increase by a slope? Could you comment on that?
Yeah. Thank you for that's a really good question. So for this project, we use 2 types of offset pressures. One's where the offset pressure is taken from the child wells, and we use those to estimate hydraulic fracture dimensions. The signals that you are referring to, they're taken from a parent well, and they are monitoring the parent-child well interactions during completion. And everybody knows and studies these fracture-driven interactions. So with Reveal, we kind of set up a classification structure, and those are the 4 classes that you refer to of, what is strong communication and what is, non-existing communication. One thing that we've learned is relying on magnitudes, it's very dangerous, and that's specifically for this kind of this project, because we have another paper out, I think it was ERTEC 2019, together with Justin Mayorga. There we showed, that there are lots of different ways you can collect parent well data. So you can collect it from the surface or from downhole. That well can be preloaded or not preloaded. And we found like 2 best practices for collecting offset pressure monitoring from a parent well. So either from a surface gauge, and you should have a preloaded well holding a full column of fluid, or a downhole pressure gauge with an isolating packer above it, because that means that you will not have a rising fluid head above the gauge that you would have if you have a large gas cap. For this project, and we mentioned that on page 6, we were not able to do either of those. So this is a downhole gauge with a significantly gas cap above it. And what that does, it can really skew the kind of signals that you see. Typically, you will see small signals at the beginning of the well, so when you're fracking close to the toe, and then as you start pushing away that gas cap, the signals they go from big to small. And that's exactly what we also see on this one. So we've stopped relying on for these kind of things on the magnitudes. It's all about the shape of the signal. So if you have a signal that comes on and then kind of curves up, those are the kind of direct fluid communication signals. That means all of a sudden that resistance between the parent and the child well is diminishing fast, and you're getting strong communications. Also, when you shut in the well, you will see an immediate drop in the pressure, because there's very little resistance of the rock in between that's kind of holding that or delaying that pressure signal. When you see pressure signals that come on smoothly and also continue to rise after shutting in the well, we will consider those as moderate or fluid migration signals. So that's basically the classification. So look at the shapes, that will tell you more than the magnitudes.
Thank you for that clarification. I hear so much about slopes and magnitudes, and I think we're all trying to figure out what is the best way to classify some of this communication. And the fact that you've mentioned about the curvature of the pressure increases is the way to determine those types of signals. I keep remembering the paper that was released in ARMA that was from Reveal Services. I think it was from Sean Spicer, and it's just the math behind the description of the offset pressure analysis. And I will be sure to include your 2019 paper that you referenced in the description, as well as the paper that I just talked about too. Yeah. So I really appreciate you clarifying that. I wanted to know, I think you answered a little bit of this in terms of the fluid migration, but there's also these smaller stress responses that are a few PSI, and they steadily increase, but I guess not a lot of people worry about those types of stress increases. At least I don't, whenever I do the offset pressure analysis. So how do you find a poroelastic stress, for instance?
Yeah, they are typically very small, and so if you see a poroelastic signal from a parent well, most of the time that means that your fracture is just passing along the toe or just passing along the heel. It's actually not, interacting with the stimulated rock volume. So depending on your azimuth, you will only find maybe a few at the toe or the heel. So they with parent well communications, they're fairly rare. We see them much more when we actually look from the parent wells. And what we do there, we isolate one completed stage. So as you're completing the child well, we'll set a solid bridge block and then complete one more stage. And actually you will have then a very small zone of interaction. And then as you're completing the offset well, so the second child well, you will see those small poroelastic signals towards that isolated stage. And then it becomes really a game of distance and overlap. So a large distance, just a few psi, and it will increase as you get closer to that isolated stage. And obviously there's a direct relation with overlap, and we use that the relation with overlap and magnitude of those isolated stages to estimate hydraulic fracture dimensions.
Awesome. I really appreciated that clarification. So there's I guess you those few the PSI increases, and then there's overlap as well. Okay. You mentioned in one of your observations that even with the reduced completion design, and it's mentioned in the paper, there is still a high ratio of direct communication responses. I was very curious on why that was the case. If you can comment on that.
Yeah, thank you. I have to look at the picture that you're probably referring to. So just for the audience, there are 3 child wells kind of in a wine rack configuration, and then there's a parent well in the upper landing zone. So we did not see any pressure communications from the furthest well. It was only from the well in the same landing zone offsetting and from in the landing zone below that we saw those signals from either fluid migration or direct fluid communication. So we did see the strongest communication actually from the well which was the closest but in the lower landing zone. That one gave the strongest communication, and it gave it consistently. So we saw either fluid migration or direct fluid communications. Also, the magnitudes, if you want to consider them, they were relatively the largest. Then from the well in the same landing zone, we saw either fluid communications, and actually from the smallest design, there was a good chunk for which we didn't see any volume interaction. And if you look at, so we classified the volumes to first response for all of those for all of those stages. So in the same landing zone, the volume to first response on average was around 4,000 barrels, and that was the smallest design was 4,300 barrels. So that's why actually it was right on that threshold, and some stages did see initiation and some didn't. The larger design was I think around 6,000 barrels. So there, for most of the stages, we actually passed that threshold. So it really becomes a game of are you just below or above what you see for volume to first response, while the closest well had volume to first response on average at 3,000 barrels. So both designs, they would respond.
Awesome. I'm really glad you clarified that in terms of why that could have been the case. Definitely a game of the amount of barrels that has been pumped, and there's a lot of factors that go into the completion design, especially with how much fluid or how much sand that was pumped. So that ratio is a higher.
Yeah, absolutely. And then if you see, for example, in those last stages, when you're in that heavy depleted zone, volume to first responses, they drop for one well to 1,000 barrels, while on average was at 3,000 barrels. So you can see really that impact of depletion even on the volumes of first response. Yeah.
Awesome. There's also, I have this internal dialogue in terms of natural fractures and being present in the area, and you may have some geologists on your team or people with geology backgrounds with natural fractures being resistive, or most natural fractures being resistive. So I was very curious that how could you tell from your technology that there may not be overlapping fracture lengths, but there could be natural fractures in the area, or that's causing communication?
Yeah, well, remember, we had two kind of offset pressure monitoring. One, we determined fracture dimensions, so length and height, and those results clearly showed that the fractures within the same landing zone from offsetting wells do overlap, but the wells from two landing zones separate, actually the heights are insufficient to, except for the heel where you have heavy depletion, but for the majority of the lateral, actually the heights don't overlap. So, you know, that's what we saw from the child-to-child well pressure analysis. When we looked at the parent well pressure analysis, actually the one in the lower landing zone, as you remember, gave the strongest signals. So we know there is kind of a difference between, you know, where the fluid is going eventually, and it finds its way not through the big fractures that you're creating, but through the reservoir as a whole, from one well to the other. While we know from, you know, the analysis of the hydraulic fracture dimensions, they kind of stay in zone. And when we later on looked at the production, that was absolutely confirmed, because the well which was offsetting the parent well in the same landing zone, it was by far the worst producer, both in, you know, early production as on later on production. So definitely it was heavily competing with that existing producer. While in the lower landing zone, although we did see parent-child well interactions, the fractures were not overlapping, and the production was a little bit lower, but it was not as much as you would see from the same landing zone. So it was really the hydraulic fracture dimensions that we have to rely on, and not so much like if you see pressure communications towards the parent well, in this case, from the during completion.
Great. Internally, we've been comparing some of the other diagnostic work along with the technology of what the hydraulic lengths or hydraulic fracture half lengths are, and it's very interesting to see those. I will admit, it's very interesting to see those results, and especially those results are converging for us too. I just wanted to make that comment, like there's so much credibility that adds to the technology that you guys have. So I just wanted to comment on that. There was also another interesting thing that I thought about when designing a job or designing an experiment. Some of the components that go into it are, you've seen so much data in a pad, but you've also seen so much data in other jobs that you've done this technology on. And I'm just curious to know if there's any statistical significance on the results between the standard and the reduced designs in the paper.
That's a really good question. So we did some studies, or actually we did quite a bit of studies. Like how many stages in A/B test do you actually need to prove statistically relevant differences? And you would be surprised that sometimes can be in the maybe 50 or 100 stages. So you need quite a bit of stages to be, you know, absolutely sure that, you know, two things that you're measuring are giving you different results. And most of the time we don't have that full luxury. And if you think about it, even if you don't change your treating design, there's a lot already going on in the pad itself. If you think about this one, you have wells that are leading or lagging with respect to each other. You have wells in the upper and the lower landing zones. You have wells next to heavily depleted or completely depleted reservoirs. So without even considering to do designs, there's a lot going on. And on top of that, you have, you know, the rock itself, which is heavily heterogeneous and, you know, drives this large stochastic behavior of results. So standard deviations in the subsurface are large. So if you have to then to deal with relatively small sets as we have here, you have to, you know, really put all the details together. And I don't think that on this path we can prove statistically relevance between the two groups. But we can start, you know, seeing some early distinctions of trends. We do see, you know, especially with the smaller design, volumes to first response actually, you know, being on the edge of the total volume pumped for that stage. So that's why we see certain stages giving a signal and other stages don't seeing a signal. So I think with respect to the volume, we can see some trends. There are also some nuances in how these stages are pumped, you know, how the sand is distributed. I think that is, we won't have the details on this path to comment on the relevance of that. So it's really the volume of sand and fluids that we can see the early trends arising.
Awesome. And you talk about early trends and you talk about those promising early trends. The other point I wanted to mention as far as early trends go is it through the production data, for instance. And I know in the paper there was 120 days worth of production data that was mentioned in the paper. So it's pretty, I mean, it's pretty good. So I was curious to know from your experience, how much is enough production data? How much is enough to make a conclusion from this work or any of the work that you've done or that you've seen?
As reveal, we have not studied too much production data because, and you know, this is maybe a kind of a shout out to the industry. If you do projects with us, also please share the production results and we'll study it in an integral way, because that is really going to help, you know, us learn as a whole. But for this project, they had production data for 27 days, and that was the early production data. And there we saw a trend of, you know, a sequence of wells of how they were producing. We also saw, for example, a significantly large water cut, really large, almost 100% initially on the parent well. And so we put all of those very initial productions together with the initial production of the parent well when it was brought online 2 years ago. So that gave us kind of the first clues of how these wells were doing relatively. And the surprising thing was that the furthest well was actually really much on par with the initial production of the parent well, which was fracked 2 years ago with a larger design. So there was this, 2 years ago, they were still on significantly larger designs than they fracked this one with. So that was the first part that we studied. And then we looked at, they did the interference test, and then we looked at another 120 days of production. And those trends of the first 27 and then the next 120 days, they really, you know, show some real strong correlations. So you have those kind of swing effects when you shut in and you bring them back online. There were some big production spikes even on the parent well. But it was really shown that those first 27 days, you could already see the clear trends that then would emerge 120 days later.
Awesome. And I do know the more production data, the better. And for us, at least that's how I've always seen it. And I was just very curious to know it's another shout out to the industry as well, that if they are going to provide production data, how much how much are they willing to provide? Of course, more the better. But I was very curious to know about what, if they want to provide production data, how much at least can they provide? I was very curious to know if you meant the chow pressure group was discussed, and some of those values were also discussed in flowing back those wells. Do you have an idea if they were drawn down the same, if the drawdown strategy was consistent? Because that does impact the chow pressure group.
Yeah. So the chow pressure group, what they started with was actually studying pressure interference between aquifers, right? And then it was converted for, you know, studying pressure interference between these wells. And they have a classification. So they say everything below 0.5 a pressure interference ratio, it's kind of a classic number, that would be weak interference, and then between 0.5 and 0.75 that would be moderate, and then above 0.75 that would be strong. So the 3 pressure interference tests that actually happened here, they all showed between 0.5 and I think 0.6. So they would all fall in that moderate category. So there's there's actually not that much difference between them, right? So even the C2 towards the parent, that was in that moderate category, and then the C2 towards the 2 child wells below, again in the moderate category. I would say these results kind of were a little bit of a surprise to us, because we were expecting, stronger communications towards the parent well, and maybe more moderate communications between the wells below, because that's what we saw from production, and that's what we saw from these child well pressure tests during completion, and it was the values of those pressure interference tests that were so close that I felt they were inconclusive. We were glad that we were able to analyze the data. It was not ruling out and not conflicting, but it was not such strong of a range that it actually gave us much further insight.
Good to know. Thanks for that insight, because the pressure interference testing is definitely a component to the outputs that you provide as a service with the hydraulic fracture lengths, and the child pressure group is supposed to provide those conductive fracture lengths. So it was very interesting to know that the conductive fracture lengths were they were pretty homogeneous from all of those wells.
Yeah, that's I think they're mentioned in a table, and there's they stay in a very narrow range of indicating moderate pressure interference.
Awesome. Well, I know I've peppered you with a lot of questions in this podcast, and there's one that I have that I can't leave you away with. And it's, what are some applications of this workflow that you haven't seen before in this industry? So
that's a good one. So I think for us, the doing the pressure interference test and having initial data and then some further production data, I thought that was very interesting to look at. And actually, after this paper, we had a strong appetite for more of this kind of analysis, where we really start making the bridge between, our completion diagnostics and production analysis, bringing that reservoir perspective on it. And I think there is, beyond the techniques that we have applied here, I think there can be applied much more techniques to really start building bridges from both sides and joining in the middle. And it really takes a team of expertise and communications back and forward to pull this together. But for hopefully this is one of a long series of where we can team up and start building those bridges, and to see how we can really correlate what's happening, what we know on the geology side of just the reservoir where we start with, how we complete it, and then what is it ultimately telling us for production, and then creating that feedback loop. So I think that is what I will be looking forward to.
Excellent. Well, Erica, it was a pleasure having you on the podcast.
Thank you for having me.
Well, you heard it from Erica. Please be sure to check out 204179, and be sure to check out what Reveal's other papers are as well. I will put the papers that we talked about in the description box for the YouTube channel and for the podcast. This is Yogashri Pradhan, and I'm signing off.